Good morning, good morning, good morning. So, whew, 2 more days, yeah, and then you get your nice chunk of break. I didn't complete our assessment from yesterday, so if you don't mind being patient until Monday, that is the goal. So, our next journey, the videos, which please.
Hello.
Good morning, sir. I believe you are the closest to the high school, Damien. I might be incorrect on that, but I'm pretty sure you live the closest. Am I correct in that? Yeah, out of anybody else. Everybody else has to travel farther, and they're here on time. I know. So just leave that couple extra minutes. Hey, plus you have chemistry. Don't want to miss a minute. Okay, very good. So, first, I want to open the floor. If you have any questions about anything that you saw in the videos, the questions on that Google form, want to make sure we're good. I wonder, do you see the answers? Okay, no worries. We killed that. There were just a couple things which I think with just a moment more thinking, you would have gotten it correct. So there were just a couple of us that chose the wrong one, just here or there. All right. So I want to address your questions first. Then the goal for me by the end of our time is that we will understand lattice energy. What is that? How do we predict which substance will have the greatest lattice energy? So that in a nutshell is what is my goal for today. You know what we'll do next Monday and Tuesday? I'll just tell you so you'll be so excited, Damien, to run, to sprint here. Lewis dot structures. Best for theory. Yay! If we remember anything about that. And if you enjoyed it before, AP makes it so much better. If you didn't so much, clean slate. All right. So first, if I could share my screen for what silly me. Honestly, and I know, David, I shared this with you the other day, probably a good 5 or 6 years into teaching, I realized like, in everyone's imagination, they don't necessarily see the same thing my chemistry brain sees. I just thought we just all kind of could see particles and could see crazy. These, of course, are kind of jokes. Yeah. If I could have you turn to the back of the front of your packet, there are a couple, I guess, comments. So I realize when I say something that I picture something, and that picture has come through years and years and years of studying chemistry, where we probably are imagining different things. Just a given. So it's understood that probably your mental model, well, if we don't talk about it, if you don't share it, it's just yours. Yeah. And you don't share with each other. I don't imagine that, like, Bryce, you say to Critton, like, can you draw for me the particle diagram of sodium chloride versus sucrose? Not. Probably, well, you are AP students, other students. And we don't get to check in. And so probably it's incorrect, but also it is susceptible to change without us even knowing it. So by your learning and so on and so on. So we need to check in with each other to make sure as we are learning from this point forward that our models are correct. We want to make sure that what we're imagining in our head is clear, that we've talked about it, that it can be used then to deepen our understanding. That's what that means. So if we could take a look at the comics. All right. Or I guess we call this comics or drawings. Okay, for example, and I definitely kind of convey this when we're talking about ionic bonding, that the metal transfers its electron to the non-metal. Well, that probably happened thousands and thousands and thousands of years ago. It's not that we're going to have a sodium atom come next to a chlorine atom. The ions exist in nature. So the transfer has already happened. They're just now going to attract each other. So it really isn't that this happens. It really is that this is happening. Whoop. This is a student generated answer. The student was asked, not one of mine, to react magnesium with oxygen to create magnesium oxide. Remember what Critton did when you heated the magnesium and we got that brilliant light. Well, here's the reaction. And then they were asked to draw a particle diagram. So what they thought is that oxygen and magnesium appeared like this in the reactant. Then you added heat, and then the magnesium separated from the oxygen. Just interesting. I guess that. Oh no, that's supposed to. What? That doesn't even make. Anyway, that's why we need to talk about mental models. So as we're going through this unit, we just want to make sure we're correct with each other. Okay, so back to my slides, and this will walk us through and address any questions you might have had from the videos. Okay, so this would be all right for mental models. This would be all right. Best example of ionic, sodium chloride, probably most common. The transfer, this gave its electron to something, sodium. We'll find it as a sodium ion. Same. Okay, let's have a serious talk. It keeps Tyler. What you need to say, Tyler, is I have Cookie Gearhart. She is going to just punch me if I'm late. And she knows I'm coming from you, so she might punch you. Not that I would, but just saying. Okay. It's electrostatic attraction. Then we have the sharing of electrons. So it is great, I think, that they're showing these, as two separate that are close together. Here, they're showing them touching, and there's like the electrons between them, and then metallic, the sea of electrons. That's a good model, series of models. Others. Okay. Ion size. We alluded to it last chapter. Are we comfortable if you want to find the colored resource that I gave to you yesterday? When a cation is formed, the cation is always smaller than the neutral atom. Always. You're removing electrons, so the remaining electrons have less repulsion. They naturally can move closer to the nucleus. Where, if we're adding electrons, there's more electron repulsion, so they'll get larger. And so this gives. We're never expected to know any of the transition metal charges, except for silver, zinc, and cadmium. But I think that this is just neat because it shares with you other common charges. Now, scandium, titanium, vanadium, they show others, but just rarely. And so that's why they're only choosing to show you one. I just think that's a little bit neat. Now, if we are asked to compare sizes of different ions, if we notice, for example, boron to neon, boron to neon, as we move to the right, we know atomic size decreases for neutral atoms. But when they're forming ions, it will be the same trend, especially because, for example, nitrogen is picking up 3 more electrons. So nitrogen is already larger than oxygen. When it becomes an ion, it's gaining 1 more electron than oxygen. It only gains 2, and so on. So we'll see this in just a moment. The same trend of size we can compare to ions. Any concerns? All right. This chart, it's just mentally wrestling with this and making sense of it yourself. And so if you had to draw this and you had to explain why there's this dip, what are we actually graphing? So internuclear distance increases, distance between our 2 nuclei. Yeah. So over here, they're not even recognizing each other. They haven't gotten close enough to feel the attractive forces. But as they get closer and closer, potential energy dips will eventually create these graphs with multiple bonds. And so if you're given where hydrogen is, well, could we sketch where an oxygen-oxygen double bond would be? How about an HCl bond? How will that be different, and so on? Questions here? All about minimizing energy. Could we identify bond length and bond energy? Okay. As far as bonding goes, so if I'm going to go back to sorry, I'm bopping around. In a nutshell, this is the series of topics of our unit. I just snipped this. The College Board directs our curriculum. It's called the CED. I just borrowed this right from them. So they're communicating to us almost 10% of the AP chemistry exam, almost 10% of the priority of our course is on this unit. So we want to make sure that we are understanding. So basically, we got that with the video information. Really, the video information and understanding that chart and bond energy and bond length. All right. Then the only thing we're really going to dig into with ionic bonding is that they form crystals. So what is a crystal? And the concept that I want us to master today, lattice energy. Sorry, sometimes I draw my E a little curvy. Lattice energy. Those are the 2 things, the only things with ionic. Then with metallic, here, let me, ionic. And then metallic is alloys. That's like a whole 3 minutes. Lattice energy, that's our focus today. Alloys, again, like 3 minutes. Then this is all covalent. So really, covalent bonding is the majority of our unit. All right. Ionic compounds, if given the opportunity, will crystallize. The overwhelming majority of ionic compounds that we come into contact with are crystals. So this is sodium chloride. So I'm familiar with that. But those are a little bit larger. Nice for us to see. Not sure the identity of this, but this is a geode. I don't know the chemical compound that's in here, but this is quartz. Example of a crystal. Not, oh, no, yeah. Not an example of iron, but that's all right. Still example of crystal. We know what crystals are. This is pumice. There's different kinds of pumice. This is not crystalline. So, what makes a crystal a crystal? We say iron compounds form crystals. Actually, the overwhelming majority of everything around us is existing as a crystalline if it's in the solid state, a crystalline solid. Even though we can't see it with the naked eye, for example, the metal that's supporting your desk, that absolutely is in crystal formation, even though that looks very different than these or the geode and so on. What makes a crystal a crystal? All right. So this is a magnification of a sample of sodium chloride. We are on page 8. Really tried to make sure that the silly, thank you. Yeah, page numbers definitely could be seen. So if we took that sodium chloride and took a hammer to it and a hammer and a hammer and hammer, we get smaller and smaller and smaller bits. Eventually, we would get the smallest building block, a unit cell. So if we could extract out, this is not a unit cell. Can we see that there's definitely organization? This is a space filling model because all of our electron clouds are overlapping. That's really, really what our crystal is like. However, for simplification, we usually use the ball and stick model, but they're not that far apart and so on. But can we see, wow, there is organization. So I have a chloride and a sodium ion. Do we understand why the sodium ion is smaller than the chloride ion? Yeah, okay. So, and when we say sodium chloride, don't we say NaCl as if it's just one sodium ion attracted to one chloride ion? But no, this sodium ion is attracted to that chloride, that chloride, that chloride, that chloride. I'm sure there's one in front of it, one above it, and so on and so on. So that electrostatic attraction extends throughout the whole solid. Now, if we could identify the smallest cube, I should have made a different color, huh? The smallest cube. And then we get the larger cube by adding other cubes together, like Lego blocks. Yeah, if you have all the same size and shape of Legos, when you put them together, you just get a bigger version of that size and shape. So a crystal has a regular repeating order to its particle structure. There are many different ways that the ions can orient themselves. So simplistically, corners of a unit cell are just really nice and simple and not crowded. But we can have something called face-centered, where they're not just on the corners, but we have an ion that's on the face of each. We can have a body-centered, and that would be if we have an ion in the middle here. So there's a varying amount of ways that the ions can orient themselves. We also can have different shapes of unit cells. And that's what's on the next page. So this variety is what gives us the beautiful crystals that in these samples we get to appreciate, right? So in this, I love this because there's multiple size crystals, but they're all the same shape. Yeah. Because of the nature of crystal creation. And there's just an example. We don't have to know, but just to expose us, there's simple qubit, body-centered, and face-centered. Those are the main ways that ions will position themselves, especially if it's a cube. Okay, so an ionic compound has organization to it. They're not just haphazardly put together. A unit cell is the smallest building block of a crystal lattice. And so we put multiple unit cells together to get eventually what we can see with the naked eye. Yeah. So a crystal lattice is definitely at least 2 unit cells. There'll be thousands and thousands and thousands. Okay. Questions? Okay. So in an ionic compound, these are ions. These are ions. Okay. So warm day. Not necessarily, but warm our hands. So we see these. Okay, go ahead and click away. Wait, we've seen these, correct or no? Yeah. I don't have enough for each one of them. So if you could share with the neighbors so they benefit, we know. Yeah. So why exothermic? Those hand warmers are a saturated, super saturated solution of sodium acetate. All right, Tyler, as soon as you see, okay, sodium acetate, what kind of body will be holding it together? You got it. And there's our cation. Here's our anion. I know too that Dylan, you're thinking, oh, Miss Gearhart, I remember we only need to know a handful of ions that when present in a compound will deliver a soluble or deliver a solution because they're soluble. So if the compound has the potassium ion, if it has ammonium, if it has nitrates, yeah, an acetate. So double. So when I make a supersaturated solution of sodium acetate, I get a beaker of water and get it to boil. Add as much sodium acetate, which is a white crystalline solid, and it produces a clear colorless solution. That's what you started with, a clear colorless solution. So what does that mean? We know the sodium ions are dissociated from the acetate ions. But there's more in solution at room temperature than there should be. So I add as much as I can at a higher temperature. Solubility of solids increases with increased temperature. And then we let them cool down. And at room temperature, your water is holding more dissolved ions than it really should be. So if stressed, hence the click, what is the white stuff? All that's in that pack. Sodium ions, and then we'd have the chin, right, of water molecules, chloride ion, and then we have the ears. It's the white stuff. Say again? Oh my gosh. You said, right, acetate. Okay, so that stress, the water is like, oh, go ahead, just attract, go ahead, because it was stressed because it was super saturated. So what is being formed in your hand warmers? Sodium acetate. The water molecules are allowing the electrostatic attraction. Why is it warm? Go ahead. Why? It's exothermic. Absolutely. Didn't we take magnets and allow them? You said, well, why does that make a sound?
Because it takes energy to like move the ion from point one to the other.
If it takes energy, doesn't that mean it's taking it in endothermic, so it should feel cold? But
because it's like because it's for positive and negative. They're not even gets taken apart and just they put it so when you take that
almost. The dissociation wouldn't happen unless there was attraction between the water molecules and the ions. Yeah, a solution won't form unless there's good attraction between the solute and the solvent. So can we say, Maddie, that like steps of solution formation, that already happened? That's what we're starting with. So we send the stress. Damien, did you have your hand up, sir? So sending the stress through, I guess if we want to imagine, maybe the stress, sending that through causes the collision of more of these. That's what I'm trying to imagine. That, oh, the electrostatic attraction, it's a full positive and a full negative. Where here, these are just, we'll learn, are called dipole ion forces. Forces where here is a bond. How could we find out or predict, or really back up why energy would be released? Yeah. So a full positive and a full negative coming together, that is much better than a partial negative and a full positive. And so when they collide and get that sweet spot distance, energy is released. All right. So can we take a look? Oh, maybe, sorry, the video's coming. Okay, so what if you were asked, well, which is going to release more energy? Which has a greater lattice energy, lithium fluoride or sodium fluoride? What if you were asked this? You see Coulomb's law, and we'll put it into practice in just a moment. Okay, so what are we benefiting from with the hand warmers? When ions come together to create a crystal, and that's what the sodium acetate is trying to do, but there's some water in the way. That's why it's kind of jelly. It is either the energy that is released when the ions come together or the energy that you have to invest to separate the ions. So we can look at it either way. This is a really, really good kind of animation of what we're talking about.
Required to pour each of those ions out from the lattice, turn them into a gas, and smoke them infinitely is the lattice energy, or strictly speaking, the change in lattice entropy. Why infinitely spaced? Well, then they're not attracted to each other anymore or repelled. Here's the definition, kind of taken from the data booklet. The entropy change when 1 mole of a crystal lattice is turned into its infinitely separated gaseous ions under standard conditions. Yeah, you forgot to say standard conditions. And there's the generic lattice energy, MAXP. But I think it makes more sense if I give an example. For example, calcium fluoride. Don't forget that on the left-hand side, it has to be a solid. All ionic crystals are solids. And on the right-hand side, everything's a gas. That's it.
So that's the theoretical definition of lattice energy. The energy you need to invest to separate the ions and create gaseous ions. We don't have to know that that is the nitty-gritty. But we also can interpret it to be the energy that is released when an ionic compound is formed. Okay, so how do we compare? I like the guy's accent. Nice to. Okay, so we need to understand that we need to just change up Coulomb's law a little bit. It's not nuclear charge and an electron. It is cation charge and anion charge. It does not matter if you have multiple of each ion to stabilize your formula. For example, Al2CO3, we still would say Q1 is +3, Q2 is -2. We look at the individual, even though we have 2 and we have 3, that's how we're going to apply Coulomb's law. And then R squared, or distance, would be the distance between the nuclei of those ions. All right. The numerator trumps the denominator. If we are comparing two substances and they are not tied in their cation and anion charges between them, we'll look at an example in just a moment. If they differ, we don't even have to think about size. We don't have to look at the denominator. If we have, for example, gosh, a +3 and a -2, and then imagine with sodium chloride, a +1 and a -1, oh my gosh, that means the numerator for aluminum carbonate is 6 times what sodium chloride would be. We don't even have to look at trying to estimate or predict or compare distance between the ion centers. Okay. Already talked about this, right? So if it's a +2 and -2 versus a +1, -1, greater numerator, this is 4 times that. Yeah.
So looking at group 1 metal fluorides and applying an equal energy source to them. Okay.
So what if they are tied? I should have prefaced, we didn't come into the audio for a second. What if they are tied? So we have +1, -1, +1, -1, +1, -1. Well, then we have to look at size.
Group 1 metal fluorides and applying an equal energy source to them. Which one's going to break first? Well, you know what? It's the potassium fluoride. That has the lowest lattice energy and therefore requires the least energy to break the ions apart. Now, why is that?
Okay, so you'll be given samples like these to judge. If there is a tie, +1, -1 in your numerator, Do you see they're all bonded to fluorides? All bonded to fluorides. So then we're only comparing the size of our cations. Q1, Q2 divided by D. So the greater the size, the lower the value of D, the smaller the lattice energy. Remember, we can call this force of attraction, the energy released when they come together, the energy we have to invest. Well, if these are cations and anions, a metal cation and non-metallic anion, then we call it lattice energy. Well, that was good. So, you can, of course, actually perform this because of the fatal consequences of having chlorine gas escape. No way, Jose, are we ever. Elemental sodium, oh, okay, but no way, Jose. So, can we just appreciate?
You did a lot until it was molten red.
If you've ever watched Nile Red,
This is back
this is him.
chlorine. It was a much more spectacular reaction.
So in the Erlenmeyer, that's chlorine. Look at that.
Demonstrations and other researches that I've seen online, I honestly expected this reaction to last no more than a few seconds. I'm not sure if I just used more sodium than the other demonstration, but the reaction seemed to go very vigorously and bright for at least a minute.
Look at all that. Sorry that your hand warmers didn't produce the light. So the hand warmer, that was just exothermic. Look at this. Obviously exothermic, but also we're getting some visible light. Oh my gosh, look, it's going. So where it started, he had chlorine gas in Erlenmeyer. Obviously, this is in a fume hood or something. I'm sure he has protective ventilation mask. And then he heated and made the sodium molten to react. It just accelerated the
As
reaction.
the reaction would die down, it's possible to see the reaction going on inside the broken test tube. Compared to the other method where it was ignited using water, this method produced a lot more sodium chloride smoke. The test tube was coated in a thick layer of nice white sodium chloride. I tried to scratch off as much as I could, but it's honestly very hard and stuck very tightly to the glass. When it's poured out, you can see that this product is much cleaner than the last run.
Okay, we can just go ahead. But so we formed electrostatic attraction, that brilliant light that was releasing lattice energy. All right, so
We took the sodium back.
okay, so how would we rank these from lowest to highest lattice energy? So we have, I'm going to stop sharing in just a second. Sodium fluoride, rubidium fluoride, magnesium fluoride, and magnesium sulfide. All right. First thing, if we are ranking or comparing lattice energies, I check my numerator. I would check ion charge, your Q1 and Q2. So, +1, -1, +1, -1. Okay, they're tied. So to be able to tell the difference, we're going to have to look at D. +2, -1. So already this is going to have a stronger or a larger lattice energy than these. Whoa, +2, -2. So without any hesitation, I know that magnesium sulfide will have the greatest lattice energy, and then magnesium fluoride. These are increasing. So I have fluoride and the sodium and rubidium. Same size. Let's say that's our fluoride. Oh, trying to make those the same size. Sorry. So what would we predict? Sodium and rubidium. Which one will be larger? +1 cation. Say it out loud. Yeah. Okay, so which will have a smaller lattice energy? Are you sure? That's all right. Okay, so we want the smallest value, so we want the largest value of D. So rubidium fluoride, it's so easy to get that flip-flop. And then sodium fluoride, and so on. Okay, lattice energy. The energy that is released when a metal cation and non-metal anions form electrostatic attraction to bond. Some of the energy is accentuated by crystal formation because that just takes more work to get everything organized and so on. So that even releases more. We can actually predict and rank and compare ionic compounds with their increasing or decreasing lattice energies by applying Coulomb's law.
Good morning, PT Jen.
Perfect
Thanks for
time.
coming.